Hello everyone, my name is Christopher Fabian. My student ID number is 2105531079 and my lecturer is Prof. Dr. Tjokorda Tirta, Nindhia. And today we're gonna talk about casting processes from chapter 3A until 3C. So let's begin. Okay, so the first one we're gonna talk about lathe operation. In general description, it is produced with a cutting action surface of rotation, and it can be both external, even internal in a workpiece. So this is the example of lathe operation. It's turning, like the workpiece is being like rotating, and the tool is cutting, like just push it. The difference with facing, it only happen in the face, but it only happen in the body. And then we have chamfering, thread cutting, spinning, grooving, drilling, parting off, boring, and knurling. Knurling is like you make a pattern of diamond on the body, and boring is like you make something like you put in the hole and you just cutting it from inside. Turning is most relevant lathe operation. In its common form, a single point cutting tool is moved on a precise path with respect to a rotating workpiece. So like what I said, the workpiece is being like rotating and the tool is gonna cut slowly on the edge of the workpiece. Form turning occurs when a single point cutting tools move longitudinally in a path other than a straight line, or when a cutting tool ground to a particular curve or otherwise irregular edge is fed radially into the workpiece. So this is just like this is the workpiece, it's rotating again, and form turning, like you have like mold, but it's just for cutting. So you put it like it's spinning, you cut it, and it's gonna make a form. And then transistor turning is a process for form turning. The inward and outward motions of the cutter as it moves longitudinally along the length of the part are controlled by a motion of stylus as it bears against a template or master part. So if you can say like turning is like just the previous turning, but the difference is just the inward and outward motion of the cutter as it moves longitudinally. Facing is like you cut it, the work part, it produces flat surfaces whose plane as it right angles to the axis of rotation of the part. As the part rotates in the lathe, the cutting tools move radially towards the axis of rotation, removing material as it advances. Grooving. The tool, usually ground the width and bottom shape required, is fed into the work, cutting a groove of the desired dimension. Grooves can be cut into external or internal surface that such cutting tool can reach. So grooving is like this. Like if you ever see on the carpenter, the block of the wood, you just push it for the cutting. And this is just kind of knurling, like what I said before, is not really a machining operation because the knurl is formed, not cut, in the workpiece. So the knurling is just make like you have like roll, but it has pattern. Like if we remember about coining and something, like yes, just coining. Cutting off is like you just do parting when parts are made in lathe. Screw machine from bar stock. The final operation is to sever the part from the remaining bar material. So that's like the cutting off. So I have a video about what we can do in lathe.
A lathe is a machine that rotates the workpiece about an axis to perform different operations, such as turning, facing, taper turning, knurling, grooving, thread cutting, and reaming, etc. To perform different lathe machine operations on a lathe, the workpiece may be supported and driven by any one of these methods. Number 1. Workpiece held between centers and tool driven by carriers and catch plates. 2. Workpiece held on a mandrel, which is supported between centers and driven by carriers and catch plates. 3. Workpiece is held and driven by chuck, with the other end supported on the tailstock center. And 4. Workpiece is held and driven by a chuck, or a faceplate, or an angle plate. The methods of holding the work may be classified under 2 headings. 1. Workpiece held between centers. And 2. Workpiece held by a chuck or any other fixtures. So today, in this video, we'll take a look at the different operations that are performed in a lathe machine.
Maybe you can see it a bit. Yeah. easy. Lathes and other turning machines. Okay, we're gonna talk about engine lathes. Are general purpose machines that provide the most basic means of performing turning, facing, grooving, knurling, and thread operations. This machine can also drill, rim, and bore. So we're gonna talk about that later. A typical engine lathe has a chuck or collet to hold the workpiece in a power rotating spindle, and a bed that normally consists of two ways. A tailstock holds the end of the workpiece opposite the spindle if the workpiece is long enough to require support at the end. So this is like the example of the engine lathe. This is the chuck, like we can see on the previous video. This is the tailstock, and this is all the in the lathe machines. Turret lathe differ from engine lathe in that they have a slide carrying a usually hexagonal tool holder, a turret in the place of the tailstock. The turret can hold cutting tool in each of its sides and can be fed longitudinally, and on some machines, transfer lathes. Turret lathes are therefore lathes adapted for production work. They are particularly suited for the moderate production level, when automatic screw and chopping machines may not justifiable, but when the turret lathes tooling arrangement permits more rapid production than is feasible with engine lathe. So this is the view from the top. From the turret lathe. I have the video here. Turret lathe. So this is the bed and tray as usual. On the turret lathe, this is the headstock, and the right side is tailstock. It has gearbox and drag and clutch control lever, fed level. Yes, this is the carriage traversing wheel, screw cutting engaging lever, and this is the fit engage. In the turret lathe is usually just using for the massive, like the amount of the production. So that's why it's more simpler than the lathe machines. Screw machines are automatic lathes originally developed for the mass production of screws. Remember that, of screws, from bar stock, but long since used for a wide variety of parts from bar stock over a broad size range. So screw machine is usually like you put it like in the head, and you have like the bore eyes. You will just make a screw. So that's it. So I have the video, you can search it on YouTube. What is the difference between CNC, multi-spindle, and screw machine? And you just scroll it from the last part of the video because my internet is lagging now. Single spindle screw machines. There are two common varieties of single spindle screw machines, the brown and the shape, or turret type and Swiss type, like we can see that on the previous video as well. The bar is held in a spring collecting the spindle. All motions of this device are controlled by cams. Cams is the one is holding the workpiece. You can see this one. Multiple spindle screw machines. It has like 4, 6 or 8 spindles instead of single spindle. You have the brown and sharp and Swiss type machines. The spindle is held in indexing drum in the headstock of the machines. The spindle has a collet that holds separate piece of bar stock. This arrangement permits the cutting action to be divided so that the portion takes place simultaneously on several different workpieces. So it has like different bar of the spindle, of course, and this is what it looks like from the view. Like this is the machine, this is the view. Yes, the previous video you can see. Choking machines. Choking machines are automatic lathes designed by operation on the casting, forging, and other parts rather than bar stocks. Mechanism of the features are similar to those of screw machines, except the bar fitting system. And this is the video that I have.
3-jaw universal chuck. In this video, we will discuss 3-jaw universal chuck. It is the important work holding device in the lathe. Chucks are used to hold workpieces in a lathe. Three-jaw chucks are used to hold round and hexagonal work. Main parts of three-jaw chucks are body, jaw, bevel teeth, scroll disc, workpiece, chuck key.
It's gonna hold the workpiece
in between the jaws of the chuck. When the chuck key is turned, all the jaws will move equal distance at the same time. The work can be centered automatically and quickly. 4-jaw independent chuck. In this video,
that's the video.
we will discuss 4-jaw
The choking machines. Now we're gonna talk about round hole making methods. The first one is drilling, of course. It's the most common tool for drilling. A twist drill is a rod with helical fluids and 2 or more cutting edges. At the end, it's rotated by its axis and fed axially into the work. As it advances, it produces or enlarge a round hole in the workpiece. The chips are carried away from the hole by the fluids in the drill. So this is like the drill size. Counterboring. Counterboring enlarges a hole for part of its depth, and usually machine is flat bottom in the enlarged portion. The operation is most often performed to provide clearance for a bolt head or multi-diameter part. So the difference between the previous one when drilling is like you making a hole, just making a hole without any like the end. If you put a screw So counterboring is used to make sure it has space between, like if you see like the nails, it has like the ends like this. So the counterboring is used for the butt of the nails. It can be fitted into the workpiece. This is the difference between them. This one basic drilling.
This has a pilot of 406 thousandths. Drilled a hole so that the pilot will fit down into the hole. And because our chuck will run out a little bit, it's okay to drill it a little under the size of the pilot, but the pilot will still fit. That way, this guides the counterbore into the hole.
Lubricant so it doesn't overheating. So this one is counterbore. You can see the difference later. So it has like the difference on how depth the thing is.
I'm going to recess this hole so that it'll accept socket head capture head and sit below the surface.
So there is a difference how they place it. So that's all. Countersinking is an operation to add chamfer the entry end of a hole. A rotating cutting tool with the edge offset to the angle to chamfer desired is fed into the hole and removes material at the edge. The tool is entered by the hole, therefore the chamfer is concentric with the hole's axis. The operation is typically used to remove burrs or sharp the edge of the end of the hole, or to provide space for a tapered screw head or other tapered object. So I have the video, the countersink here, but we can make it quick by this is the countersink hole and this is the already counterbore. So if you see the difference between this, the angle of the hole is like this one is flat and this one has like some amount of degrees. Now we have reaming. Reaming is a secondary machining operation for existing holes. It can provide more accurate diameter, improve straightness, and smoother surface. So it like you make the clearance of the previous, like if you already make drill, like other things, you can use reamer. They can use guided by bushings to slightly improve the hole's direction or location. So this is one is the reamer. You can make it more clear and get in the screw. That's all. Now boring. Boring is an operation that enlarge and improve the accuracy of existing hole. Remember that is different, totally different from the drilling. The difference is when you make drill, it makes the hole, but the boring enlarge and improve the accuracy of existing hole. That's all. We will continue. Jig boring. Jig boring is performed on jig boring machines, which are vertical boring machines of very high accuracy. The table movement is extremely accurate, and the spindle bearings are very precisely made. The machines are mainly used for making jigs, gauge, dies, and fixtures, especially where accurate layout and hole location are essential. So the tool motion like this. This is the work part. This is the work part as well. So the hydro. This is like the work part, and the jig boring is like it has like knife, and it cutting like moving rotary, so it moves like this. That's all. That's the jig boring. Horizontal boring mills are basically large horizontal milling machines capable of performing boring mill and other machining. And that's all. That's actually just boring mills, but it's horizontal. This is the sample of the video. So it's like making hole on the workpiece. Vertical boring mills are machines with a horizontal table rotation on a vertical axis and precision tool head, capable of movement up and down, side to side. There may be more than one cross slide with tool holding capability. These machines can be considered to be large slates turned head on end. They are especially suited to boring and other operations on parts too large for conventional weight. Gun drilling is shown in figure 3b6, like we can see on the left here, is a rotating single flute drill, normally carbide tipped, is guided by a bushing at the start of the drill hole and is self-guided thereafter by a bearing surface opposite the cutting edge. A hole through the wall leg of the drill provides a means for oil coolant to flow at high pressure, the cutting edge, and to flush chips from the hole. So this is the typical of the gun drill. This is the video.
Deep holes can be drilled conventionally on a CNC machining center, MEC for short. For a hole to be drilled precisely, a pilot hole is required. First, the surface of the workpiece should be machined perpendicularly to the hole center line. Then, a pilot hole has to be made for startup to a drilling depth of 3 times the hole diameter. This ensures that the gun drill is guided during startup. The actual drilling is carried out in up to 3 work steps. During the first step, the maximum drilling depth which can be reached is 40 times the hole diameter. Then a second, slightly smaller drill must be employed. With this, whole 80 times the depth of the hole diameter can be drilled. The third drill is smaller once again and extend the hole to a depth of 1 or 20 times the diameter.
So let's see all the gun drilling. Tree panning. Tree panning is make a circular groove in a workpiece through the use of one or more cutters, cutting teeth, rotating about the central axis. If the grooves are cut all the way through the workpiece, a hole is going to be created, and a circular centerpiece called a slug is produced. The process is used primarily for large shallow holes. It is also used to machine round disc, bone flat stock, and illustrated in Figure 3b. So it's gonna make a hole. It's all. Multiple spindle drilling. When production quantities are sufficiently, it may be justifiable to construct a drilling head with a number of drills, all of which are driven from the spindle power source and make contact with the workpiece at the same time, drilling a number of holes simultaneously. There are three basics of the spindle drills: adjustable, geared, and gearless. The adjustable variety use universal joints so that the drill position can be varied and are desirable for moderate sized loads. So this is the video.
This is a multi-spindle head drilling attachment, and what we have is one input here that is attached to, in this case, the radial arm drill press. It's a Morse taper, and as it rotates, what it's doing is it is interacting with several U-joints down below, and they will drive different drill bits. These drives are on U-joints, which allows us to set the drills at different diameters by the means of adjusting it on these elongated slots. The drills will each drive, and then down below what we have a jig. In this case, the jig is set up to cut 6 holes at a diameter and 1 center hole. If you wanted a different configuration, you would have to make a different one of these jigs. So the multi-spindle drilling head is up here, and then the jig is down below. So what we'll do is we'll put a piece of plate in the jig, and we will drill a hole pattern on it. So it'll go in. We have some locking tabs here. Okay. Now what we'll do is we'll turn the drill press on, and we'll run this. I'm running it just a little bit slower because I'm not using coolant, and I want to leave the coolant off so you can see what's going on. Okay, we'll engage the feed. Okay, so the holes are now drilled. Loosen the stops, get that plate out. and have a look at it. So ideally, this would be done for mass production where you have a lot of
grinding and abrasive machining. At the point where the cutting takes place, grinding is very similar to other machining operation. The difference being the workpiece is cut by sharp edge of a small piece of abrasive materials. If you know grinding, it's like you're grinding this and it's gonna get like cutting because the material is very sharp. And if you remember what is sharp is like your DH, or the material is really like it's not smooth, so it's really hard to move. Cylindrical grinding is used to produce external cylindrical surfaces by removing material, creating smoother surfaces, and providing more precise dimensions. In all such operations, both the grinding wheel and the work created. The grinding wheel moves towards the workpiece to contact it and away from the work after the grinding is complete. However, in many cases, the wheel also transfers the work, or vice versa. Center type of cylindrical grinding. So we just gonna jump into the videos because it's easier. And the grinding wheel normally rotates on axis parallel to the axis of the workpiece. The wheel of the workpiece contract to rotate so that the contracting surfaces move in opposite direction.
Construction details of cylindrical grinding machine. A cylindrical grinding machine has headstock, tailstock, chuck, cross-feed hand wheel for table movement, grinding wheel, base, work table.
So the one that being water is like the grind here. This is the grind. So the purpose of this grind is to make it more
grinding machine.
Like more smooth. Centerless grinding is a process of machining cylindrical surface wherein the workpiece is not held between center or in a chuck. Instead, the workpiece is supported by a work-rest blade at the correct height and contained between two wheels, as shown in figure here. So that's the just grinding centerless, like different from the previous one. So this is the video.
External cylindrical grinding.
I need to skip this because I cannot like just go to the point. So centerless grinding, it has like three types: through feed grinding, range grinding, and internal grinding. The difference between them you can see here. The through feed grinding is it has like regulating wheel with the different angle here and the work rest blade here. So the work part is gonna go through the two roller grinding wheel and regulating wheel and also hard work rest blade. Range grinding is just like a normal one, and the internal grinding is like you make inside the workpiece. Internal grinding, like we saw before, is a process for finish machining existing round holes. It normally is performed on a lathe-like machine. The workpiece is held in a chuck or faceplate holding fixture and rotated about the axis of the hole to be ground. The rotating spindle carrying the small grinding wheel is inserted into the hole, and then the fed radially to contact the surface. So that's it. Surface grinding, it moves the workpiece in a horizontal plane so that it passes under the revolving grinding wheel, which contacts it and removes surface material. The result is a part with a flat, smooth surface and accurate thickness or height, as we can see on the right here. So it like happen in horizontal, and grinding it's gonna be happen like rounded, but the workpiece is just standstill. Jig grinding. Jig grinder is a precision vertical spindle machine similar to a jig borer. It is used for internal grinding. It has a horizontal table that can be moved and located very accurately. The spindle head contains high-speed grinding. Remember that head that rotates the grinding wheel about its axis, but the axis also revolves in planetary motion. So this is the video.
For almost a century, Apex Toolworks has been a master of manufacturing's toughest challenges: designing and manufacturing precision tooling, machining precision parts, and engineering and building components, assemblies, and systems to the highest tolerances. In the course of doing all this, Apex has developed specialized capabilities rarely matched by others. One of these unique capabilities is high-quality, close-tolerance jig grinding on the largest
So
scale.
jig grinding is like the drilling, but it just moves around the edge of the hole. Low stress grinding is a variation of conventional grinding in which objective is to minimize stresses developed in the workpiece by the grinding operations. It differs from conventional grinding in the very low wear, in-feed and down-feed rates. Frequently dressed quartz, softer open-grain wheels, and liberal flow of the coolant are also used. Plunge grinding is simply a center-type operation that are no transfer feed of the grinding wheel. Instead, the wheel is fed directly into the work. So, if the wheel dress free to form the ground in the workpiece, if the wheel grounds area is more than the width of the wheel, the operation can be referred as the plunge grinding. So this one is the video, plunge grinding. So the plunge grinding is gonna be held on the chalk as usual, and the grinding is gonna be like around the workpiece. It happens in CNC. So this one, okay, this one is the grinding. I mean like the grinder here. Now it's gonna be moved on the very like stabilized move. So that's it. This grinding is a means for producing flat surfaces. The workpiece is held against the flat side or face of a large rotating abrasive disc. As you can see here, it holds on rotating abrasive disc. So we just jump to the video.
Consider one of the classic grinding processes. Double disc grinding is performed when both sides of a workpiece must be ground so that both surfaces are exactly plane and parallel.
So remember that the grind of the opposite surfaces of the workpiece at the same time, thus controlling flatness, thickness, and parallelism in the same operation. Abrasive belt grinding uses an abrasive cloth belt to remove metal. The endless belt runs between the drive wheel and contact wheel, and the workpiece bears against the belt. So if like you ever see like someone who sharpen their knife using like rotating system like with belts. So that's all. Abrasive jet machining. Abrasive provides the effect finely powdered abrasive in high velocity of stream of the gas or a liquid. The stream is directed the desired place on the workpiece. So actually, if you see this one, it like this. It has like high velocity of air or gas, and abrasive particles, of course, for cutting things. So this is the video. It makes hole. So that's it. Abrasive flow machine. Abrasive flow machine is like it's pretty hard to explain this one, because pretty like abrasive medium which is pumped in the workpiece. The abrasive particle medium rub against the workpiece, gently removing surface material. The process is used to round sharp corners and remove burrs. Burrs, if you know, like it like you're cutting something and it's not smooth. So this is the video.
For more than 20 years, Engineered Finishing has refined surface finishing with breakthrough technologies, including abrasive flow machining. With increased part complexity, closer surface finishing tolerances, completing a part becomes expensive when using traditional methods. Manufacturers are faced with high reject rates, low productivity, and minimal consistency from part to part. The question is, how can these problems be avoided or eliminated?
So actually it's like, I'm gonna explain from the picture. So the mixture here, abrasive media, just push into the workpiece. So the workpiece is gonna like have some space to make the abrasive media is going out. So it's gonna be smoothing the holes. Ultrasonic machining utilizes an abrasive water slurry and a shape tool with the abrasive between the tool and the workpiece. And this is just like the normal ultrasonic one, and it's gonna be like the fixture here and the tool here, and workpiece on the here is just gonna be like you're gonna put ultrasonic machine. So the frequency, it makes the vibration to abrasive particle against the workpiece, cutting a cavity that has the same shape and the tool. So that's all for the video today. Thank you for watching and see you next time.